In this video we're going to talk a little bit about why we spent so much time on energy in the previous videos, and really this video is going to be talking about a gentleman named Niels Bohr, and we're going to be talking about the applications to a model that he came up with. That's very important, and hopefully by the end of these videos you'll see why we spent so much time on frequency. But if you do remember from the last video, we talked about frequency, we talked about waves and whatnot, and we remember that frequency is equal to the speed of light in a vacuum over the wavelength. Now, when we're talking about electromagnetic energy and how much energy is released, originally this equation was good because it let us know the frequency of a wave, and it gave us an idea on the size of that wave, but it doesn't necessarily describe in the units we're looking for how much energy is released, because remember, this is in hertz. So there is an equation that we're going to be talking about that involves using the frequency equation to incorporate energy, and the equation for that is going to be E equals h nu. And all this h is this h is just a constant, and it's known as the h is known as Planck's constant, named after the father of quantum mechanics. And the constant, and it's okay if you can't remember this because it's kind of a complicated number, is 6.626 times 10 to the negative 34th, and I believe this is kilometers over times meters squared over seconds squared. So it sounds really complicated, but really all this is doing, this number, is it's taking the frequency that we've discovered, and we're just putting it in terms of energy. And by doing that, we're able to alter the units a little bit so they're more favorable to us. So really, another way to write this equation, if I wanted to write it a little bit differently, I could say E equals h times, and then I could sub in for frequency, I can sub in the c for the speed of light, and then this can all be over lambda. Okay, so this really is the formula we're going to be looking at when we want to talk about how much energy the waves that we're looking at are giving off, essentially. That's what we're talking about. Okay, so we have two constants in there, and really one more thing that I want to talk about is note that the energy is inversely proportional to the wavelength. Remember, we used these terms before. This is basically just saying that as the wavelength gets bigger, the energy is going to come down. As the wavelength gets smaller, the energy is going to get bigger, and the energy is going to be proportional to the frequency, which again is, you can see that from the E equals hv, they're proportional to each other. So when one goes up, the other one's going to go up. Okay? So let's move down here a little bit, and let's talk about Mr. Niels Bohr. And really what he did was he developed a model for the hydrogen atom, which, if we want to talk about where hydrogen is, hopefully you're kind of getting familiar with the periodic table, but hydrogen is our first atom here. And the model that he developed explained what's called an emission spectrum. Now remember, when we have our energy levels here, this, if we were to say this was our hydrogen energy levels, we have the energy level n equals 1 here, and then we have n equals 2, and as we go out, as we go further, we have more and more energy for our electrons. N equals 3, and n equals 4, and so on and so forth. They go further out. Here's n equals 5, n equals 6, and what Mr. Niels Bohr did is he was able to see that instead of the energy being continuous, instead there was specific spots where if you measured the frequency of the electrons that were emitting energy, they had a specific wavelength that would always be the same. In other words, this the bottom one here, the hydrogen emission spectrum, is only for hydrogen. Only for hydrogen. So, in other words, this is almost like the fingerprint of the atom, kind of, is one way to think about it. These are like the fingerprints of the atom to help you identify the atom. And this not only applies to just hydrogen, but his theory actually applies to, so it applies to hydrogen, it also applies to helium plus and lithium 2 plus. And the reason for that is if you look on the periodic table, when you remove an electron from helium, you're left with 1 electron. If you remove 2 electrons from lithium, if you remove 1 electron from helium, you're left with 1 electron. If you remove 2 from lithium, you're left with 1 electron. I'm sorry, guys. 1 electron. So his theory really only works for if we have 1 electron, because we also have 1 in hydrogen. If we didn't have lithium 2 plus, it would actually have 3 electrons, and his initial theory wouldn't have applied. So what he's saying here, to simplify, is by measuring what happens when an electron goes down in states, because remember, emission, the electron is going down energy levels and it's emitting this energy. And what he's doing is he's taking all of these different spots. So here's n equals 5, and here's what color we're doing it, n equals 4, and so on. And as you're going down, he's measuring the wavelengths of each one of these spots as the electron's emitting energy, and he's basically recording it and then showing what the waves look like. Now, not all of the waves are going to fall into the electromagnetic spectrum. Remember, we talked about the only waves that are going to fall into the electromagnetic spectrum were under the visible light spectrum, which I believe was 10 to the 14th to 10 to the 15th, approximately in this range of frequencies. So some of these you're not actually going to see. That's why when you look at this spectrum, there's really only 5 different lines that we see between 400 and 700 nanometers. Okay, so let's take a look here. So this is the spectrum of hydrogen, and one other fancy term they throw around a little bit is this Lyman and Balmer series, and also the Paschen series. What this is saying is that the Lyman series is any energy that jumps from a higher energy level all the way down to the ground state. So that would be all of these. Any energy that jumps all the way down to the ground state is going to be in this Lyman series. Are we going to be able to see these on the spectrum? Will it come up as when the electrons emit the energy? Will it come up as one of these colors? They won't, because the smallest, the shortest wavelength we'll see is the violet, which is 400 nanometers. Anything before that is not going to be in the visible light spectrum. So we're not going to see these wavelengths because they are so much smaller. They're going down so many more energy levels, down to this first energy level. The second, if we only go down to the second energy level, then that's called the Balmer series. And if we go down to the third, there's the Paschen. These are all named after famous scientists. But the ones that we're mostly focused on is this Balmer series, because these are all the waves. If you look at the range they're in, I mean, really we're talking about 410 to 656 nanometers. Those all fall into our range of visible light, which is right around 400 to 700 nanometers. So these are all the waves that we're really measuring when we're talking about visible light. These waves still exist. These waves, when they're emitted, still exist, but we're just not going to see them. So one more time, what's basically happening is I have an electron. We're going to say we're talking about my electron here. Let me do it in a different color. This electron here, and when the electron loses energy, it drops down state, and as it's dropping down, it's emitting a wavelength. Now, how come this wavelength is 94 nanometers, but this electron over here is 410 nanometers? Why is it different? And the reason for that is because this first energy level this is not drawn to scale. Not to scale. It's just here to give you an idea. This first energy level, in reality, if we were to try and hit our point home, it's more of something like this. Here's your first energy level. Here's your first energy level. And, if it was here, the n equals 2 would be over here. N equals 2. And then here would be the n equals 3. N equals 4. And you kind of see what's happening here. So these energy levels are a lot closer together, and these excited states are going to get closer and closer as we go this way. And then there's going to be this huge gap here between between the ground state and the excited state, and this is a lot larger energy difference. And even this diagram is still not to scale, but it's closer than what you're seeing over here. So when the electron has to jump this much farther, or actually come down this much farther, it's significantly more energy. So it's more energy. And remember that when energy goes up, what happens to the wavelength? So what happens to this? Well, when the energy goes up, the wavelength is going to be smaller. So that's why these wavelengths are so small, because the energy is coming down a lot further away. And you can see this is 122 nanometers. This entire path from I think this is the n equals 5, all the way back to n equals 2 is just 410 nanometers. So there's this one energy level between the ground state and the first excited state here, which this would be n equals 2. There's a huge gap here that's so much more significant than all of these other energy levels, that when an electron comes down from that energy level, it's tremendously more energy that is being released than it is even if you're coming down 4 energy levels here at this 410 nanometer mark. And if you didn't believe me, you said, "Oh, I don't think that's right," you could test it. You can take 410 nanometers, which would be, let's see, 4.1 times 10 to the, what's that, -7th meters, and you can put it in to this equation, and you can see how much energy is being released. If you wanted to compare, okay, how much energy is being released by this electron versus, this guy over here, you can put them both into the equation and you can test it. And you will find, let's see, 94 nanometers, that would be 9.4 times 10 to the -8th meters, right? You can put them both in and you can test it, and you will find that this energy here is going to be a lot higher. You're going to release a lot more energy from this than you would from this electron, because they're inversely proportional. In the next video, just because I don't want this to run too long, we'll start to talk about what this emission spectra means, a little bit about this absorption spectra, and we'll continue to move forward in our discussion of just some basic applications of electron kinetics.